the population of adults in the U.S. have a bachelor's degree or higher. Create a probability table for the number of college graduates from any group of 7 randomly selected adults. What is the probability that a sample will have 5 or more college graduates? All right, we can totally do this. So what this is asking for is a probability table that looks something like this. So here we have K, right? Number of bachelor's degree people, right? And that could be 0, 1, 2, 3, 4, 5, 6, 7. And we also want to know the probability where x equals k, right? And so that's going to be, well, we could just find out those formulas. So just to give you an idea, I'll show you the first one. We could do probability of x equals 0, right? 0 number of successes. That's going to be n choose k. So n is 7, k is 0, right? And just to remind you, 0 factorial is just 1. It's not 0. Times the probability of success, which is 29, to the 0th power, and 1 minus 0.29 to the n minus 0 power, right, which is just 7. 7 minus 0 if you want. It's just 7. All right. So, oh, you know what? I wonder if there is a, oh, I think there is. Let's look up choose and see if choose means what we think it means. Oh, no. Unfortunately, choose means literally like choose a number. So this is not exactly what we want. So sometimes it's useful to try. Sometimes I try like combine, maybe combination, right? So let's see what this one says. This one says the number of items, that's like n, and the number of items in each combination, which is k. Oh, and perfect. This is exactly what we're looking for. N factorial over k factorial multiplied by n minus k factorial. This is exactly it. So we want to choose, for number, we want to put in n. For number chosen, we want to put in k. So we can use combine. Great. Oops. Okay, so before I do that, I'm just going to create a little table for myself so that I can stay sane. So here's 0, 1, 2, 3, 4, 5, 6, 7, so that I don't have to put in my formula again and again, but I could just copy and paste, right? And then P, where x equals k. And so in this case, it's going to be combine 7, 7, and I want to make it a formula, so I'll choose that 0 right there, times 0.29 to the 0th power. And Excel knows order of operations, so it's going to do the power before multiplying, right? So it's going to do the exponent before multiplying. And 1 minus, oh, I need to put that in parentheses though, 1 minus 0.29, because multiplication will go first, right? To the 7 will always stay the same. That's why I'm just typing it in. Minus k power. All right. So the probability of having 0 people have bachelor's degree is 9%. And then I'm just going to copy and paste that all the way down. And we could see, you know, that 9% might look small, but that's larger than all 7 of them actually having bachelor's degrees, right? And we are looking, let's see, for what is the probability that a sample will have 5 or more college graduates. And here we can use the addition rule to put these three probabilities together. So just to show you, just going to get rid of this over here. So I'll just write the 5, 6, and 7 probabilities. So this is 0.0217. This is 0.0029. Oh, that's going to be round up to be 30. This is 0.0002. Okay. So here you could obviously fill in the rest, but what is the probability that a sample will have 5 or more college graduates? Well, we could put together what is the probability that X is greater than or equal to 5 or more, right? And so that will be the probability where X is equal to 5. 5 plus the probability where X is equal to 6 plus the probability where X is equal to 7, right? And so I'll bring this back. If I just add these up, the probability where X is greater than or equal to 5 is the sum of these three, and we get 0.0248. 0.0248. So that means just like 2.5% chance of randomly selecting 7 adults and finding that at least 5 of them have a college degree. Ta-da! All right. Although this seems like it would take a really long time, it's sort of brainless to like plug it in. So that's why it's like I'm just showing it to you on Excel. Obviously, you could write this formula out for each row of these and then calculate it by hand. But Excel comes in real handy during those times. All right. So 40% of blood donors have type A blood. The blood bank needs 2 type A donors to walk in, like desperately. The blood bank will test 10 random donors and count the number with type A blood. So if they say count the number with something and it's like one or the other, right? Then binomial distribution. What is the probability that the blood bank gets fewer than 2 type A donors? So if they had said, what's the probability that blood bank gets 2 type A donors versus type B donors, this would no longer be a binomial distribution because you could be type A, B, AB, or O, right? But this is just saying, what's the probability that they're A or not A? And so that's how you know it's a binomial distribution. Okay. So what is the probability that the blood bank gets fewer than 2 type A donors? Well, it's nice to just start off with this idea that there's, 10 donors, right? And 2 of them need to have this type A blood, right? And so that would be, the probability for any one of these combinations would be 0.40, right? That's P, right? To the kth power, so how many? We need 2, right? Times 1 minus 0.4. 60% is the not A probability. Times to the 10 minus 2 power. So that's the rest of the slots, the other 8 slots, right? And then we need to know how many of these combinations we have. So that would be n choose k, which would be 10 choose 2, right? So this would give us the probability where x equals 2. But is that what this is asking? No, that's not. So this isn't good enough. What we really need to know is the probability where x is fewer than. Oh, so not even fewer than or equal to, just fewer than 2 type A donors. Right? Because these are the situations that they really don't want, right? So how do we get this? Well, that's going to be the probability where x equals 0. I should have probably done this first. Plus the probability where x equals 1, right? And so we could find that. And if this is x equals 2, we could obviously do this for x equals 0 and x equals 1, right? So this would be 10 choose 0, 0.40 to the 0th power, and 0.6, the not A probability to the 10th power, right? And also 10 choose 1 to the first, to power of 1, and 0.60 to the 9th power, right? The rest of the slots. And I could just use my handy Excel function, now that I know combine. And we'll put 10 choose 0 times 0.4 to the 0th power, which is going to be 1. So I don't really need to put that in, times 0.6 to the 10th power. I don't know why I'm putting it in parentheses. It just makes me feel cleaner or something. All right. So that's the probability of getting 0 out of 10. So it's pretty low. It's less than 1% chance. So it's 0.24% chance, right? So we're not in super danger of that happening. But let's look at the probability of only one person having type A blood walking in. That times 0.4 to the power of 1, which is going to be just itself, and then 0.6 to the power 9, and that is a 4% chance. So if we add these up, then what do we get? Still, just a little more than 4%. So this would equal, so why don't I put this here? So this would equal 0.0427, right? So a little more than 4% chance that that the blood bank will get fewer than 2 type A donors if 10 donors walk in. So those are pretty good odds. They don't have to be super worried. All right, example 4. 2.4% of students in a large state university considered themselves multiracial. In a random sample of 100 students, what is the expected number of multiracial students? What is the standard deviation? This is a good one because this is definitely a case where you cannot imagine, well, even with 10 blood donors, you couldn't imagine. But, 100 for sure, it's like you cannot, that would spend like way too much of your life writing down all the different combinations. So this is a really good example of situations that you run into where you're really going to need these binomial distribution ideas. All right, so what is the expected number of multiracial students, right? Well, we could make this giant probability distribution, right, of 0 to 100 and find all the probabilities and then like do the expected value thing. Or we know that there are some regularities to the expected value in a binomial situation. So, all right, so we could also write it as mu sub x. And we know that this is n times the probability of success, right? Whatever success is, right? And here, success is being multiracial, right? And so our n is 100. And what proportion of that will, what proportion of those students will be multiracial? It's just 10 times the probability of success. So times 0.024, that's 2.4%, right? And so that's 2.4, right? Exactly, yeah. And so the expected number of multiracial students, around 2.4, and that makes sense. All right, what about standard deviation? Standard deviation. So that would look like this with the sub x, right? And I always like to start with a giant square root. It just helps me remind myself where I'm going. Sometimes you could put it in at the end, but I don't know. Sometimes I forget to put it in. So n times the p, so the probability of being multiracial, but you also have to account for probability of not being multiracial, right? So that would be 100 times 0.024, right, times the other side of that. So that's the 97.6%, right? So 976, right, of not being multiracial, of being, I guess, uniracial, right? And so that's really 2.4 times 0.976, right? So I'm just going to use my handy-dandy calculator. So 2.4 times 0.976. So that's 2.34. And the nice thing about standard deviation is that it's always in the same units as the mean. And so if this is 2.4 students, this is 2.34 students. So the spread is quite small. I mean, given that it's a 100-student sample.